They're highly dynamic structures showing flows and oscillations pretty much all the time. They're formed, as I said, over shear magnetic inversion lines in the solar magnetic field. And they're also signs of much larger structures, referred to sometimes as a filament channel or the coronal cavity. And these are actually the more basic structures, I think, in the sun as far as the magnetic field is concerned. And filaments are basically where we see these. And I will talk about that more as we go along. Okay, so some basic questions about prominences that we need to understand. And all these three questions relate to other areas of solar physics. And so they're really tied in with things we need to know about the sun in general. One question is, we need to understand their magnetic structure and how that evolves, both on the level of the prominence itself, but also in a global way connected to the global solar magnetic field. We also have the question of how does a cool material come to be in the corona? And this relates to larger questions, for instance, related to coronal heating and dynamics in the corona and chromosphere. And then we have the question of what causes prominences, and of course on a larger scale, coronal mass ejections to erupt. And so all these are really central questions to solar physics. Of course, I could not possibly cover all of these things. What I will do is at least touch on some topics related to the first two questions, and then I will leave out the very large questions related to eruptions. So I'll just be talking about just the non-erupting prominences here. Okay, so again, some basic characteristics of prominences. This is sort of my stereotypical prominence I'm showing here. Some vocabulary. In general, prominences generally have sort of elongated sort of ribbon sort of structure, and I'll refer to that as the spine. And then off to the side, they have these sort of pointy structures that actually extend down to the chromosphere, and I will refer to those as barbs. Sometimes they're also called feet. As I mentioned before, prominences form over polarity inversion lines. So you'll have one magnetic polarity on one side, the other on the other side. The prominence field, though, actually has a strong component along the inversion line, but it's not exactly along it. So if you actually look carefully at like the thin threads that form a prominence in a high resolution image, or you can see this with the barbs here, the actual structures and thus the field in the prominence are sort of at an angle, maybe say 25, 30 degrees to that inversion line. The barbs actually are attached to areas of what's called parasitic polarity, small areas where the magnetic field is different than what it is on that side of the inversion line. Okay. And as I said, the prominence are sort of symptoms of these inversion lines and what's called either the filament channel, if you're looking at the chromosphere, where even when the filament isn't there, you can see structures that indicate that you've got this sheared magnetic field. Also, if you look in the corona, you'll, for a prominence that is in a quiet region, you'll often see sort of this dark area here called the coronal cavity, which is the three-dimensional extension of the prominence into the corona. And these structures, the filament channel and the cavity, will be there without the prominence. The prominence is just there. Sometimes it'll be there, it'll disappear, maybe it'll erupt and reform. But you'll see these structures showing the underlying magnetic field. They're more permanent. Okay. All right, so some of the characteristics of prominences. Prominences exhibit a sort of a handedness that's referred to as chirality. It's also related to the helicity. If you're standing on one side of a prominence or a filament channel, and you have the positive polarity on your side. If the sort of general horizontal field is going to your left, that's referred to as sinistral. If it's going to the right, that's referred to as dextral. Now, it isn't too regular thing to actually measure directly this field, so this is determined by characteristics of the prominence. For instance, if the barbs will go one way for a sinistral filament, the other way for dextral. If you look at the overlying arcade of field lines that go over the prominence, they'll actually be going the other way, as you see here. And if you look at this carefully and think about the barbs and actually also the threads and the prominences going this way, the overarching arcade going this way, that implies sort of a spiraling helical type magnetic field. And so this is sort of the handedness in that structure. And if you have that kind of magnetic field, you'll have this handedness. The reason it's interesting, though, is because there's a pattern to that. And it turns out that regardless of solar cycle, you'll tend to get dextral filament channels in the north and synestral ones in the south. So this is a global pattern that's something that has to be understood and incorporated into any model of the global magnetic field. Also, filament channels have certain patterns that they fulfill over the solar cycle. In general, prominences that are occurring in and around active regions show the standard butterfly diagram type structure that you can see here, but also the ones that are near the poles will exhibit this sort of race to the poles phenomenon that you see that's used as a marker of the reversal of the sun's magnetic field. So again, the prominence and again, the magnetic fields in the channels are associated with these global structural events. Okay, so there are historically a lot of different ways to categorize prominences. I generally think of them in pretty simple terms related to essentially how strong the magnetic field in the environment is. So you have active region ones that occur sort of in and around sunspots. Quiescent just means it's forming in an area that's quiet. Intermediate, sort of between the active regions or in the decayed active region. And you can have one prominence that's more than one of those things along its length, like this example here, where you've got something going right through an active region and it extends out into a quiet region. So you might classify this as active in one area and intermediate in another. And this is interesting because they have somewhat different characteristics depending on where you're looking, again, that are related to the magnetic field. In an active region, prominences you usually see mostly just sort of spine. You won't see too many barbs in general. Lots of long, thin threads. This is from Hinode SOT, and the authors are mostly paying attention to this sort of interesting spiraling pattern. And I'm just pointing out, though, the long, thin threads. Again, this is very characteristic. And flows and that sort of thing. Magnetic fields, maybe 100 or so, or a bit over 200 Gauss, something like that. Okay. Quiescent prominences often are not too different, really. Here's an example of a quiescent prominence. You have a long spine, but you usually see these barbs here. Like, you can see them in here. This is actually the same prominence on the limb. And you'll see, again, long flows, thin threads. Then you'll see these sort of vertical-looking structures, and these are just the barbs. When you get these to the limb, you're looking along here, so you have more optical depth along the structure. And you'll see these, they kind of look, especially in the AIA data, sort of like trees. Lately, there's been a lot of discussion of these in terms of solar tornadoes, which is an old term that's kind of been resurrected. I don't actually like the term used for prominences anyway. It implies things like rotation that some people are arguing that they're rotating, but I do not think that's established. And so I do not like that term. But in any case, this is a pretty typical way a prominence might look on the limb. Now, there's another, though, element which is related to that cavity that I mentioned before. And if you look in a prominence for instance, this is an EUV image from AIA, and here we're looking right down the polarity inversion line effectively. If you look carefully, you can see the prominence on the limb along here, on the disk. And then when we get up over the limb, you see all this structure, and this might be an especially nice example, but this is not uncommon. And you can see all this emission here that's sort of going up into the prominence. You see these sort of loop-like structures. If you're looking at Doppler data, you can see shifts that form these sort of rounded structures like this. And what this is showing is the overall, again, magnetic structure that's three-dimensional, goes into the corona, and the prominence is just sort of the stuff down here But it's associated with all this stuff that's higher altitude and larger scale. And I think understanding prominences and just looking at the cool emission is just a very small part of the picture, really. And it's sort of an historical part because you can see the cool material from the ground. But now we've got really nice data showing what's going on up here. And that, I think, has to be part of our understanding. Okay, so the standard magnetic field models for prominences take that basic helical structure into account. And here's just an example of a flux rope model for prominence. And the purple lines are the actual magnetic field. The sort of orangey gold is our current sheet. But what I want to call your attention to is these dark areas, which are areas where the magnetic field has dips. And so these are marked out. And basically the idea is that you see sort of a long, dark ribbon-like shape. Here it is from above. And that would correspond to the filament or prominence. And so the basic idea is, okay, you have this large-scale structure, but any place where you have a dip, then you can basically have your cool material, if it can get up there, will stay in the dip and hang out there. One thing to notice is that in most sort of current models of prominence magnetic fields, you notice this is just winds once in this image. You don't get very many ones before they erupt at any rate that are sort of going around and around and around. It's usually just sort of, this is just one loop. This is another possibility, which is this is actually a sheared arcade. So you don't actually have a full turn here. You just have shear on either side of the inversion line, but you still get this sort of twisted structure up in the corona. And again, if you mark out the places where there are dips, you get a sort of a long ribbon shape. That's the prominence. This is, again, the same thing, but you're only seeing the dips. And here, where this is actually a flux rope model, where the parasitic polarities off to the side have been included, and you basically get the barbs. So if you look at this model from the side, you get a long spine, you get barbs going down to the chromosphere, and that looks a lot like what we actually see. So that works pretty well as a general model. There are some questions. This is spectral polarimetry data related to the magnetic field. So I'm showing two different examples. On the left here, you've got, these are barbs here, and this is data from Tamis, and the one to focus on is this plot here, which basically shows the inclination angle, which is pretty much at 90 degrees, so it fits well with the sort of idea of the prominence being in the dips, and that's mostly definitely what you get along the spine, and for the most part. But there have been some observations where they think with other, this is from the German Vacuum Tower Telescope, using a different spectral line, where there's a suggestion that maybe the fields aren't horizontal, that you might have sort of a spiral shape. So I think that's something that has to be resolved. These are different prominences, but I think it would be interesting to see analyses of the same object with both kinds of observations. But still, in general, I think there's a general feeling that kind of prominence, we kind of understand what the magnetic field is. Maybe there's some questions. But when you get to something like this, I think people are more unsure about what's happening. I don't know how well this is showing up in the back. This is from Hinode SOT, and this is something you might typically see in prominence near the polar crown. So we're talking about relatively low magnetic fields for prominence, maybe 3 to 10 Gauss. And if you can see this carefully, you see that the structure tends to look more or less vertical, but it's very sort of turbulent looking, and you see things look like flows going up and down and sort of vortical shapes in the flows and these sort of bubbles like you can't, sort of down here. And these have been known for some time, but I think the Hinode observations really brought those forward, that this is something that's interesting that we don't understand very well what's happening in prominence. Okay, and This is a Dopplergram showing that those aren't even really vertical motions as they appear, that they're actually coming in and out of the plane of the sky as well. That makes it even more complex. So a lot of work has been done on these. The one I'll highlight that's gotten the most attention is the idea that these might be some sort of Rayleigh-Taylor instability. And this is the actual data here showing these structures that you get, and then this is a simulation by Hillier et al. Also the idea that Kelvin-Helmholtz shear flow instabilities might be involved as well. But I think there's still a fair bit of work that needs to be done on that. Okay, so another important question is, what is the origin for that cool prominence material? Just to go over a very basic argument that I think was put to rest some time ago. There's not, I mentioned before that we've got this sort of low density cavity all around the prominence, so hey, couldn't that be the source of the prominence mass? It's got low density, maybe it's just all into the prominence, but there's just not enough mass for that to work. We need another source of prominence mass that's not just sort of the ambient corona. Ultimately, it has to come up from the chromosphere in some fashion. The question is how. So there are a number of different suggestions that have been made. One of them is the idea that prominences are caused somehow by jets, some sort of jet, probably a cool jet that shoots material at chromospheric temperatures up into the prominences. Especially in active regions, active region prominences, there are a lot of papers where people see that. You see a lot of jetting and flows like that in active regions, so perhaps that's a possibility for those. Some people have suggested this, though, for all prominences. And I should say going in that I think the sheared inversion lines are sort of an environment where you can get these dips. So it doesn't mean there's only one way to get cool material up there, but if it does get up there, any place where you have dips in the field lines, you'll tend to collect the cool material. So it might be more than one of these options are at play. Okay. Another possibility is a class of models referred to as evaporation condensation models. And in these you have magnetic field lines, kind of magnetic loops, and you have just heating down at the foot points. Then you get evaporation of the chromospheric material heated to coronal temperatures, goes up into the corona, and eventually gets to a high enough density that you have rapid cooling and condensation. And this kind of model has actually been developed rather extensively in the form of a thermal non-equilibrium model. This is an example of that kind of cartoon I showed applied. It's a one-dimensional model I'm showing here, but it's applied to a sheared arcade model with many field lines. And here we're looking right down the inversion line. And to the left, we have an H-alpha proxy. And so this is actually our prominence forming down here, relatively low down. And this is what you might see in a coronal temperature line in AIA. And I hope it makes you think of that movie I showed earlier of AIA, where you saw all this sort of looping structure up above the prominence. So that's something I like about this model, is that it does tie into that sort of coronal picture of prominences. This model would work better with longer field lines, so it might be better off in a quiescent region sort of prominence, might be more effective. Here's another variation I mentioned. This is basically a 1D model. Here's a model by Shah and Keppens, where they're actually doing a 3D model of the same process. And in addition to getting the material up in the corona using the foot point heating and condensation, in this model, you also have Rayleigh-Taylor instability causing cool material to flow down out of the prominence. So you can sort of combine these different processes. Another option that people have suggested is a levitation sort of model, where you have the field moving cool material up into the corona. A really simple version might be just having a flux rope emerging and bringing material up with it. This is actually difficult to do if you just bring a flux rope right up. All that material that you're bringing up as it comes through the photosphere would tend to keep it from moving upwards. Most of the actual models of this have reconnection down low, bringing the material up, is in this cartoon here. An example of a model sort of along these lines is this recent one here from Kaneko and Yokoyama, where actually they have two arcades that are reconnecting in the low corona. And as they reconnect and bring up this just low corona material, the reconnected field lines are longer. And this changes the conduction properties, and you end up getting condensation. Sort of like in the condensation models, but getting material up in a different way. So it's just showing some of the variety of different ideas people have had. And recently people have suggested that sort of turbulent looking motion in the polar crown prominences might also be bringing hot material up, and then it might condense in the prominences as well. So there's still a number of different ideas that are out there. Okay, so just to go over what I've been talking about, so we have the questions and prominences about what their magnetic structure is and how it evolves. We know in general that the structure is sort of a basic helical type structure. There's still people working on details of how that forms, how the different possibilities are related, and then of course how that relates to global evolution of the solar magnetic field. There are a number of different ideas out there about where the cool material comes from. So we still have questions about which model is actually valid, where is it valid, where in the filament itself is it, are these things happening? If we have jets or we have heating along different field line foot points, is that happening everywhere along the filament channel? Is it just happening some places? Why? What is the origin of the fine structures that you see in prominences? They really do have fine structures down to about the limits of a resolution, and we don't really know why that is. I guess that's related to similar questions about coronal loops, perhaps. And as I said before, I'm not even getting into the issue of eruptions. I hope we'll have some interesting talks about those tomorrow. And just to mention, just a couple years ago, there was a sort of an overall review volume about solar prominences published, and so if you're interested, there's a lot more detail. They said I felt like I've really been skimming the surface of this topic in this talk. And there's also a Living Reviews solar prominence observation paper that came out not that long ago. So.
Thank you. Well, I'm going to talk about the temporal behavior of MIT waves in a partially ionized plasma when the plasma is heated or cooled. Well, on the left-hand side, you have seen this movie in the previous talk. This is a quiescent prominence, in which we can see a lot of dynamical features, like upflows, downflows, and so on. So it seems, in general, prominences are very dynamic structures. But on the right-hand side, we have three panels which belong to the same prominence, and you can see large-scale oscillations propagating in the vertical direction in the body of the prominence, with periods between 20 and 40 minutes and speeds about 10 kilometers per second. These oscillations were identified as magnetoacoustic waves, so what we have is MSD waves in a very dynamic, or a highly dynamic medium. On the other hand, prominences are heated or cooled by chromospheric and coronal radiation, but at the same time, they cool by radiation. For instance, due to heating, prominence can disappear in H-alpha and reappears when it cools down. These phenomena were called thermal disappearances and reappearances, and it seems that the main cause is the ionization or recombination of hydrogen. Also, an interesting feature of this phenomena is that the cooling process takes longer than the heating process. Then, when the temperature of the prominence changes, the ionization degree also changes, as well as other plasma parameters like conductivity, resistivities, etc. and this influences the behavior of the MHD waves. So our goal here is this one, to study the temporal behavior of MHD waves in a partially ionized plasma with prominent physical properties in which the temperature changes with time. We consider a very simple model, a spatially uniform and unbounded hydrogen plasma with a magnetic field, a horizontal magnetic field. We neglect gravity, and the background state is given by these expressions. The temperature is a function of time, pressure is a function of time, and density is constant, and magnetic field is constant. We use the single fluid MHD equation, continuity equation, momentum equation, the energy equation, where E is the specific internal energy and L represent the sources and sinks of energy, equation of state, and the induction equation. And in the induction equation, we have the classical resistivity and also ambipolar diffusion. Eta C is the Cowling resistivity. The specific internal energy of a partially ionized plasma is composed of two terms. The first term is the standard internal energy, is this one here, and the second term is the ionization potential energy, in which we have in the numerator the ionization potential, in this case for hydrogen, the atomic mass unit, and this quantity is the relative density of ions, which is related with the mean atomic weight. Then we take into account the background state. The energy equation is given by this expression, in which the interplay between heating, cooling, and the temporal variation of the mean atomic weight determines how the background temperature evolves with time. We need the temporal behavior of the mean atomic weight, and this has been calculated using the Saha equation. We know that this is not fully realistic for prominence because we are assuming local thermodynamic equilibrium, but this is the most simple way to do it. And we assume a constant heating per unit volume, and we consider two different processes. In one case, a heating process in which the temperature goes from 4,000 degrees to 9,000 degrees, and a cooling process in which the temperature goes from 9,000 to 4,000 degrees. Between these two temperatures, the plasma is partially ionized, is always partially ionized. For 1,000 degrees, the density of ions is very small, so we have a lot of neutrals. And for 9,000 degrees, the density of ions is very high, but we still have neutrals. Then, to get the temperature profiles, we solve numerically Saha and energy equations together with an initial condition for the temperature, and we obtain the time-dependent temperature profiles. In this panel, I show you the temperature profiles for the heating and the cooling cases. Heating is the blue line and cooling is the red line. And what we see is that in the heating process, the temperature increases, but ionization takes place. So part of the energy is going to ionize hydrogen, part of the energy is going to increase the temperature, and you see that this line is not going up in a straight direction, is distorted a bit, but the heating process takes a short time to arrive until we arrive to the final temperature. In the cooling processes, we decrease the temperature, but recombination takes place, so that means energy is released to the plasma. So the plasma, for the plasma, is much more difficult to cool down, so it takes longer to arrive to the final temperature. On the right-hand side, I show you the temporal behavior of Cowling resistivity, which is an important quantity, at least for Alphen waves. And we observe that during the heating process, we start with a very high Cowling resistivity, which increases very rapidly until a final value. And in the cooling processes, we start with a small value of the Cowling resistivity, and it increases, but it takes also longer to increase until the final value. We want to study the temporal behavior of linear MHD waves, so we impose a small perturbation on the background state, and we assume the perturbation behave in this wave, so we have Fourier analysis in space, but not in time, and we obtain the time-dependent linearized equation for fast and slow wave, which are coupled equations and are shown here. This is the energy equation, which is very complicated. And also for Alfvén waves, the case of Alfvén waves is more simple, and we can combine these two equations to obtain a single differential equation for Alfvén waves. Here, the dissipative term is this one, which involves the Cowling resistivity and the classical resistivity. Well, we have studied wave by wave. First of all, the Alfvén waves. We consider Alfvén waves propagating parallel to the magnetic field. We impose a value for the parallel wave number. Is a value related with the values of the number of observed improminence oscillations. And we seek for a numerical solution with this initial condition. The damping of the Alfvén waves is due to Cowling resistivity only because we only impose parallel wave number, so that means in this dissipative term, this term is 0, so we only have this term. And in the left panel, I show you a comparison between the behavior of the velocity amplitude for Alfvén waves during the heating process and during the cooling process. What we see in the case of the heating process, which corresponds to the blue line, is a strong decrease of the initial velocity amplitude, and then the velocity amplitude becomes more or less constant. The reason is we have initially a high value of Cowling resistivity, but Cowling resistivity goes down very rapidly. We attain the final value of the Cowling resistivity, and then the Cowling resistivity is small, so it takes a long time to damp the oscillations. In the cooling process, what we have is a small value of Cowling resistivity at the beginning, so we have weak damping during very long time, and finally, when the Cowling resistivity arrives to the final value, the damping becomes more strong, and then the velocity amplitude is completely damped. The right panel, we have a zoom for a time interval of 100 seconds in order to see the rapid damping in the heating process. So we start here, and after more or less one oscillation, the velocity amplitude has decreased to almost half. We also can see there is a difference between the period during the heating process and during the cooling process. It's slightly different, the period. From a WKB solution to the differential equation, we can obtain approximate expression for the period and the damping time. So in the case of the period, we have plotted here a comparison between the period in the heating and the cooling case. So you can see that most of the time the periods are very similar, only at the end of the time interval considered the period in the cooling case evolves and increases rapidly. But the important difference is in the damping time. The damping time depends on the Cowling resistivity. This value has been fixed, so the temporal change of the Cowling resistivity is giving the behavior of the time damping in both processes. So in the cooling process, we have very long time initially, then it decreases, but still is long. Instead, for the heating process, we have a short damping time initially, and then it increases. So with this approximation, we can understand what we obtain in the numerical solutions. For fast wave, we have solved the couple MRT equation for a slow and fast wave. We impose perpendicular propagation in this case, and the initial conditions are these ones. And in this case, the temporal damping is due to Cowling resistivity and thermal effects. You look to this panel, you can see that this looks very similar to what happened in Alfvén wave, but there is a strong difference because the damping is strong, because we have thermal effects. So initially we have, for the heating process, the strong decrease of the amplitude, and then this is not completely horizontal, it's going down. So at a certain moment, thermal effects become dominant, and then the damping is dominated by the thermal effects. And the same happens for the cooling process. The damping is weaker, but the thermal effect, they play a role also here. Finally, we have solved the same equation trying to get the velocity amplitude for slow waves. We assume parallel propagation in this case, and in this case we only have damping by thermal effects. And here we compare the velocity amplitude for the cooling process, or during the cooling process, the red line, and during the heating process. As you can see, the periods are different, the damping are different, they are not in phase, they behave in a different way. And if we want to understand what happens here, we need also to look for an approximation. We have computed an approximate dispersion relation, which is here. This is the sound speed, but this is the non-adiabatic sound speed, which includes the thermal effects, which are changing with time, and also it includes the mean atomic wave, which is also changing with time. So this is a non-adiabatic sound speed with many terms. And from this expression, we can compute the period and the damping time for the cooling and the heating process. What we see is different behaviors, which explain the different damping time for the heating process and for the cooling process, and also the same for the period. They behave in opposite, they have opposite behaviors. Conclusions. Well, during heating or cooling processes involving ionization or recombination, it is important to take into account the ionization potential energy term in the specific internal energy when you compute your energy equation. The interplay between the radiation, we have assumed optically thin radiation, heating and the temporal evolution of the mean atomic wave determines how the background temperature will evolve with time. In our computations, the cooling process takes longer than the heating process in agreement with some observational results. Finally, a proper interpretation of the oscillation observed in a very dynamic prominence plasma is not an easy task because of many effects which can be involved there. But it is needed in order to perform meaningful prominent seismology. Thank you for your attention.
So, hello everyone. I'm going to talk about the first paper that I just published as a part of my PhD. I'm doing the PhD under the supervision of Professor Astrid Veronik at the University of Graz, and I'm happy to talk about this collaborative work that we've been doing together, and I think it's a very nice one. So, thanks first to Temuri for giving me the chance to give this talk here. And well, this is the outline I will be following during the talk. I will give a very brief introduction because I don't think I should talk about the standard model of a solar flare for half an hour since we only have 15 minutes, and then I will just jump into a case study and I will just talk about the main results of the paper. So as we know here, for the standard flare model, here we have a figure by Shibata et al. In 1995, and it explains how an erupting filament stretches the solar magnetic field in the corona, and oppositely directed magnetic field lines are drawn towards each other, and a current sheet is formed where magnetic reconnection sets in and a large amount of energy is released. Electrons are accelerated in that region, travel toward the denser solar chromosphere, and hard X-ray emission is observed as a form of ribbons, or quasi-parallel ribbons is what we called. But the thing is that this model is a bit, it's a bit limited when explaining other kinds of ribbons. And here we're interested in circular-like ribbons, such as this one that we see down here. And these kinds of ribbons are usually generated, they usually have a very particular photospheric magnetic field. So we see here a circular-like polarity in white, a batch of negative polarity or parasitic polarity in the center. We already heard the term in the first talk. And then we see at a remote location a patch also of negative polarity, just like in here. So we see that the magnetic configuration in this model, we see here what we call the outer spine, which is the magnetic field between this remote location and a 3D null point, or nearby the 3D null point. We see the inner spine, which is the magnetic field emerging from this parasitic polarity until the vicinity of the 3D null point. And the magnetic field here spans, opens up and closes around the circular-like polarity in what we call the fandom. This is taken from the Masson et al. 2009 paper, and also this one. And we see that this is a figure in 1600. And we see that we have a circular-like ribbon here as the intersection of the fandom with the lower atmosphere. A very compact ribbon also as the intersection of the inner spine and the chromosphere, and a quasi-parallel ribbon as the intersection of the outer spine and the chromosphere. So we wanted to study a similar case in an attempt to understand what triggers these kinds of flares. And our flare was, or our event was selected because the ribbon pattern was a bit different from what we are used to see. And it exhibit a time delay in the formation of the ribbons that made us think that other possibilities other than electron beams for the generation. So the date of the event was January 29th, 2015. It was an M2.1 flare. And we see here that we have a sunspot followed by a group of smaller sunspots. And here in the line of sight magnetic field, we see that we have a horseshoe-like negative polarity encompassing a patch or a positive polarity or parasitic polarity. And then at the location of the sunspot, we see that we have positive polarity. So it seems like the photospheric magnetic field is that of a circular-like ribbon event, so to speak. We have a figure in 1600 at the time of the impulsive phase, and we see that 4 main ribbons are generated, and we call them R1, 2, 3, and 4 for later reference. But we see that these ones that we will later call primary ribbons are greater or larger in extent, and the secondary ribbons are a bit shorter in extent. Okay. So this is a figure. Here we see the ghost light curve, and here we see the Resi count rates for the different energy ranges. And we see in orange here the 25 to 50 keV, which is mainly non-thermal or pretty much non-thermal. And we see that during the impulsive phase here, we see these 3 hot X-ray bursts that basically should correspond to the time when the electrons collide with the chromosphere. So it basically should be that, right? And here we have the a sequence of 1600 and 304 Armstrongs. And we see that here these dashed lines are represent each of these 3 panels, and this one was later on. It's not represented here because Resi entered nighttime at 11:50 or 11:52 or something like that. So this was later. So we see that during the early impulsive phase, 2 primary ribbons form, and then only in the mid-impulsive phase, the secondary ribbons start to form. And only later, all of these ribbons are developed. So we see that at the beginning, we can say that this is kind of a quadrupolar ribbon structure. But if we compare this to the 304 sequence, we see that later on, this develops into a quasi-circular ribbon flare. It's just more prominent in EUV than UV. So I have a figure of, if I can play it, yes. we see how the ribbons are formed. And this circular-like polarity is visible here. We do see something here, but it's not so prominent in UV, so that's why I plotted in UV. So this is a time sequence also. Well, this is only pre-flare, and this is decay phase, the early and late decay phase, in order to assess what, let's say, reconnection did to the flare. And we see that here at the location where the primary ribbons form, here we see a group of reconnectors, sheared arcades, that are visible in all UV channels. They're visible in all UV channels, so it means that they're not only hotter, but also visible in the hotter channels, but also denser, and therefore visible also in 171, for example, which is a cooler channel. And we see also that here, where R3 or one of the secondary ribbons form, we see these loops here that in the hotter channels, or the hotter channels brighten. It means that they're hotter during the decay phase than during the pre-flare phase as a consequence of heating. So here we see a sequence in 94 and in 1600, only for the region where the primary ribbons form. I will come to that, why we plotted only this region later. And overplotted, we see the 6 to 12 keV in purple and the 25 to 50 keV resi sources in orange. And we see that during the pre-flare, there's already thermal emission, and the plasma is of about 9.6 megakelvin. And during the impulsive phase here, we see that the plasma temperature almost reaches 20 megakelvin, and there is a loop-like, let's say, structure in the non-thermal, as a non-thermal source. So the reason why we plotted only the primary ribbons is because we didn't observe any resi sources anywhere else in the sun. So not only, we didn't observe anything at the location of the secondary ribbons, but this may be because the resi dynamic range is 10 to 1, so maybe the imaging algorithm cannot image very well weak sources. And as we saw at the beginning, R3 and R4 are a bit weaker than R1 and R2. But the thing is that the timing at which the secondary ribbons were formed, it was really a bit later, and the peak intensity was really a minute later of the hard X-ray burst. So if we see here, like for the primary ribbons and for the secondary ribbons plotted here in black and in blue, and here for comparison, the 25 to 50 keV, we see that for the primary ribbons, especially for 171, the light curve closely resembles the hard X-ray bursts. This doesn't happen with the secondary ribbons, in which the maximum intensity is reached 1 minute after the third hard X-ray burst. So also we have that there's somehow a faster decay for the primary ribbons than for the secondary ribbons. In the secondary ribbons, we observe there's a cooling time of about 5 minutes, and that made us think that maybe there's another process involved in the formation of the secondary ribbons. So if we see only this region, so this is R1, 2, and 3, and this is C1 outlining here a loop, we see that there's kind of a flow-like structure here and here that later on approaches the R3, and when it arrives at R3, R3 is generated. We also observe it in 131, in 171, and in the rest of the channels. Actually, I have a movie here, and if we see here they're generated, and the secondary ribbon is formed at this location. And sorry for this is not a very good movie, but we see it very well in 304. So for this other region here, or 1, 2, and 4, we selected another loop, C2, and we see that also, move it here. And we see that also for this case, we'll see a structure traveling along this loop and brightening up this region here. So in order to estimate the velocities of those flow-like structures, we did a time-distance plot along C1 and C2. And here we see the Resi count rate for the pre and impulsive phase. And we see that these traces represent the the flow-like structures that extend well into the pre-flare. And actually there are signatures already detectable at like 11:23, which is about 15 minutes before the onset of the soft X-rays. So we observe that the speeds are below, here we say there's a 240 kilometers per second, but we corrected that velocity, taking into account the angle at which that structure arrives in the chromosphere, and the speed is actually 630. So the speeds were all below 630, and we measured acceleration and deceleration of these structures. And we also decided to do an intensity increase analysis. And we see that in general, for these structures, the intensity increases of about 30 to 40%. And for R3 and R4, the increase is much greater. So two possibilities are possible. Either they are flow-like structures or disturbances, or slow magnetosonic waves, for example. So de Mortel et al. In 2002 published a paper in which 38 events in which slow magnetosonic waves were observed along loops, and these were the main results. So these disturbances were observed only in 171, and only for 2 cases they were observed in 195. The speeds were found to be below 165, and the intensity increase was always below 10%. And none of these things were registered. On the contrary, in our event, we see that our structures are multithermal, the speeds are much greater, the intensity increase is more than 3 times what was reported before, and we do observe downward motion, acceleration, and deceleration. So, are they plasma flows? So if they're plasma flows, we can calculate the thermal peak energy at the location of, let's say, R3, and we can compare it to the kinetic energy of the supposed to be plasma flows. So we did it for this plasma structure, which was the fastest one and the most prominent one. And we took this box of 12 arc seconds in length and 3.6 arc second in width, and we assumed also that the depth was the same as the width. The plasma temperature was found to be of about 3 megakelvin, and the emission measure increase, as can be seen here, is of about 1.5 times 10 to the 27th. And we also calculate, since we're here, we also calculate the increase in density, which is of about 20%, which is of about more than 3 times what was reported before in literature. The peak thermal energy at R3, okay, thanks. The peak thermal energy was found to be 10 to the 27th ergs, and the kinetic energy only for this plasma structure was found to be 8 times 10 to the 26th ergs. So it's not the same, but this is only for one plasma structure. So if we add up the rest of the plasma structures, like let's say these 2, it's already pretty much this energy. So we do think they're flows, plasma flows. And just something I will not extend here, but here is where R3 is formed, and we see that this is an image of the pre-flare environment of the magnetic field. And we see, and a preliminary analysis already showed a 3D null point at this location. And we do not see any connection between the null point and R3, which one would expect if R3 was generated by the electron beams. So, very quickly, so in summary, for the primary ribbons, we observed a group of reconnected sheared arcades, resi-thermal and non-thermal emission, strong time correlation between the UV brightness and the thermal count rate, and direct magnetic connectivity between a null point and the primary flat site, indicating that the primary ribbons were formed due to magnetic reconnection. However, for the secondary ribbons, we didn't observe any Resi sources. The maximum UV emission of the secondary ribbons comes later, much later. We observed the multithermal plasma flows. The kinetic energy correlates to the thermal energy, or R3, and there's no direct connectivity between the position of R3 and the null point. So we think that the plasma flows generated during the pre-flare compress the chromospheric material at the secondary flare sites, dissipating its kinetic energy and causing R3. And that is it.
So, in fact, I will speak about the white light flares. As you know, the first white light flare was observed by Carrington many years ago, and still we don't have idea what is the mechanism, what is the real mechanism of white light flare. Some people claim that all flares are white, but we are not able to detect it, perhaps. But we are speaking also of mechanisms. So how the energy is deposited in the layers of solar atmosphere, which are able to radiate in continua. So there are at least two ways. One claims that the energy of accelerated particles is deposited direct in the dense layers of photosphere, while the other claim that it's not true, that the photosphere is formed by backwarming from the chromospheric layers. So, and it is also a way how to classify the flares. In fact, on the magnetic stars, large flares were registered, and during the large flares, changes in the Balmer continuum flux was registered. So a new measurement by Kowalski in 1913 reported of increase of Balmer continuum in such flares. So here on this picture by Kowalski et al., you can see the red and blue lines. So it is those are the models, and the black curve is measurement. So you can see here in the wavelengths, which is close to the Balmer jump, that the change of continuum is very well detectable, and it's comparable to the models. Of course, we tried also to make measurements on the sun, but it's not so easy because the contrast, or when you measure the radiation of the sun as a star, is very low because the size of flaring regions is very small one. So we raised these questions, and when we started to think about the new method of measuring the radiation, and we found after several years, of course, that it's possible, and I will speak here about how to do that. So we used for measurement a ground-based telescope, which is in Ondřejov. It is this one, and here's the optical scheme. And what we used was only the celostat and also the main telescope. And here we put the device, and the device looks like that. So here is an optical scheme of that. So here you can see the telescope, and here, of course, it's not in the scale, but here is practically the focal plane, and we select only a small part of the sun disk, and only this part which is selected comes through the optical fiber to a spectrometer. And also a part of this beam is reflected, and we use it for making H-alpha picture of the situation on the entrance diaphragma to the system. So here is how it really looks like. So here is the small spectrometer. In fact, it's possible to have those spectrometers from this size, from this wavelengths, and we selected as a first step this blue continuum region with such a grading. So we have about 3 pixels per angstrom. And here is how the Clyde-Sun registration in this spectrometer looks like. Those are the calcium lights. Then we decided to move it to another telescope, because in the previous one it was in competition to multi-line observation of solar flares and prominences. So we decided to improve an old telescope, which is here in the old part of the observatory, and one of the advantages is that we have it all the time to our measurement. So it takes us about 10 minutes to start it and to observe. And now it's made like a almost automatic system. So you just come there, open there, you calibrate the system, you set up the active region, you select the diaphragma and the exposure times, and you put it on operation, and you can go along according to other tasks, and it will work for you automatically. So here is how the system looks like. So here is the focal plane of the telescope, and we put there a system which consists of the optical wedge, which is here in front, and also from a wheel with diaphragmas, and they are 7 of them, and they have several sizes. So you can select the one which fits best the size of active region. And this system is used for taking pictures on the sun. So you can see here a flare, and you can see here the ring, reflecting rings. So it is this one or this one, and only the light which comes through the ring take part in the measurement of spectral flux. So here is one flare which was measured. I mean, it was this one. It was X flare, and so it was this one. And the flare area on the diaphragma was only from 4 to 7% of the surface, while the flux contrast there was about 17 to 21, even more percent. So here is how the Clyde measurement in the sun looks like, and here is the increase during the flare. Again, Clyde, so it's in various parts. It's raw data, and here are data which are processed like that. The flare measurement minus quiet sun divided by quiet sun. And here is the measurement in this interval. So it's from 8:42 to 9:09, and it is when the seeing effects are removed. Sorry. So you can see here that so here are the calcium lines, and you can see here sudden rise of the continuum flux during the flare, during the first part of the flare. And you can see that it comes sometimes to more than 20%. just now going down. We decided to have another spectrometer, and in addition to the blue measurement, which is from 350 to 480 nanometers, to measure also the other part of the continua until 920 nanometers. And here is how the measurement looks like. It was measurement just a week ago, and it was on a quiet region, which was on the western limb. So we can see here any changes in the parallel continuum or in the partial continuum lines. So now what we are going to do, we are going to do not have only the relative calibration, but also to have at each time of the measurement the absolute calibration. So we use the peak atlas of the spectrum to compare the quiet solar disk with our measurements. And we suppose that all the data acquisition in process are linear for each wavelength. So we will use interpolation for particular position on the solar disk, and we use also the length tables for each individual wavelength and position on the sun. So we think it's a very simple and but perspective tool for measuring solar continua. So as a summary, so we developed and constructed and put in operation a new device for measuring blue continuum and also all optical continua, and it's put in operation in Ondřejov. We still measured three X-class flares, and the changes in blue continuum during the flares was detected. Of course, we don't know until now what is the size of the kernel flaring in those blue continuum. But knowing that, we could be able to also derive the intensity of the radiation. Just now, we improved the feeding telescope, and data acquisition will be complex and practically automatic, and we suppose that the precise calibration of the data also will be solved. So here are references. So it's the method was described in this paper on solar physics. Then we have also some work about the processing of the data, and now one paper which is also using this data. The first author is my former student Ondřej Procházka, so it also uses the data. So that's all, and I hope I am in time. Thank you very much.
From our published paper on the dynamics and energetics of transverse waves in coronal loops. This is a work in collaboration with my supervisor, Professor Tom van Dorselare, and Patrick Andolin from St. Andrews. So the outline of this presentation is quite straightforward, to be honest. We just set up the problem, then we explain how our models look like, we present the results, and hopefully we'll have some discussions at the end, hopefully, or not. So, why transverse oscillations? Well, they're pretty much everywhere. Since 1999, we have observed the standing modes, propagating waves. We have observed them in various lines. We know that they're getting dumped, and they act, they're a pretty good way, an efficient way to transfer energy up to the corona. And this is our end goal, to see how we can dissipate this energy and hopefully get some heating in the corona. Well, this is my most text-heavy slide, so the rest will not be like that. I'm just want to list here some of the damping mechanisms that we have studied over the years. Well, not me personally, but the whole community. So we have the mechanisms of resonant absorption and mode coupling, which are pretty much similar mechanisms, and what they do is they explain the energy transfer from the global transverse motions of these waves down through resonance to shear local azimuthal modes in the boundary layers of flux tubes with which we simulate usually the coronal loops. Apart from these two mechanisms, we have phase mixing, which is a way to create smaller scales from the interaction of out-of-phase alveolar waves in inhomogeneous plasmas. Now, outside the main damping mechanisms and acting in parallel with them, for the standing modes, we have the development of Kelvin-Helmholtz stability. The theory behind that was developed pretty early on, but in the last few years, we have done extensive work, both mainly numerical work, on the development of Kelvin-Helmholtz stabilities on flux tubes, and this has been applied to coronal loops, to prominences, lately even to spicules by Patrick. And finally, well, the dissipation mechanisms, because all the previous mechanisms, what they're doing is bringing down the energy to smaller and smaller scales, but after a while, after some point, we have resistivity and viscosity taking place, and this should actually dissipate this energy and hopefully lead to heating. I'm saying hopefully because this is still under debate, the way I see it. So the main hypothesis of our work lies in this slide. Back in 2014, Patrick Andolin et al. Were studying the development of apparent strands in flux tubes, and as a line of sight effects due to the development of Kelvin-Helmholtz instability, and which we now call the development of tweak rolls, transverse waves induced Kelvin-Helmholtz rolls. Catchy name, if you ask me. So the first picture we see is from that paper from 2014, and we show the development of the Z vorticity up top and the current density on the second panel. And by looking at these two, this image, Patrick Andolin et al. Suggested that in the vicinity of the tweak rolls, we would have viscosity and resistivity acting as the main dissipation mechanisms. So we would have ohmic heating due to the currents developing there, and we should also have viscous heating due to all the velocity gradients developing at the tweak rolls. Working on that, in 2016, Magyar and Van Torselare found something really interesting. Studying the energy at the layer of a flux tube, they realized that the rise of the internal energy was much less than the rise of the temperature in that layer. And their suggestion was that we can explain that only because of the mixing taking place, since they considered a setup where the temperature outside of the loop was much higher than the temperature inside the loop. The mixing taking place due to the Kelvin-Helmholtz stability led to this rise in temperature. And this is where we step in. So we again use a straight density heavy flux tube. We have a magnetic field along the loop axis. We study the ideal case, but unfortunately we have numerical dissipation, which will have to act as resistivity and viscosity, or both, or one of them. We'll see later on. We have two different types of models, a model with a uniform temperature everywhere, so that we can address directly the heating mechanisms, if any. And we have also a setup with a temperature gradient, similar as Antolin et al. 2014 or Magyar van Dorselaere 2016, that would be a nice contrast, and we can use them to study the mixing effects. The density profile we use is again from Antolin et al., as you can see in the upper picture on the right. The loop length, the loop radius are again similar to that work. We have a resolution of around 30 kilometers in the XY plane, and we have estimated the Langwist number to around 10 to the 4. This is the effective Langwist number due to effective diffusivity, and this was done through a parameter study after we obtained our results. Now, in our setups, we have we consider two different cases again. One with an initial pulse, like it was commonly used up to that point, and two models where we, instead of an initial pulse, we have a driver acting at the foot points. And we want to use this driver because we want to give energy in a consistent way over a long period of time and see how our system would evolve. We use the MPI-MRVAC to solve this problem, and we have set the period of our driver to be approximately equal to the theoretically predicted one for the fundamental kink mode. This is a summary of our different setups. So, uniform temperature and a driver driven equal T from equal temperature, uniform temperature initial pulse standing equal T, and then we have the driven diff T from the temperature gradient. Not my best choice of names, but it's quite descriptive. In the second picture, we see these setups at work. Now, let's go to some results, shall we? On the right, we have the typical standing oscillation due to an initial pulse. It's what we expected it to look like. Nothing new there. On the left, however, we have the case with the driver. What we observe is that initially, the waves, we have waves propagating from the foot point throughout the loop. Now, we have considered symmetry, so there is the half of the loop is not shown here. But we have counter-propagating waves, pretty much. And they superpose, they form a standing mode. And due to the frequency that we chose, this standing mode looks like the fundamental one as it's shown on the right. Now, what I would like you to notice is the elongated structures developing, especially at the driven case. They look a lot like the work from Antolin et al. Over the apparent strands. And you can see that also in the next slide, where I'm doing some forward modeling. This is just a small attempt. I'm not going to get into details there. We're using the FOMO code, or forward modeling code, developed by Tom in Leuven. And we are showing the 193 angstrom line. And what we can see here is that, like in Antolin et al. 2016 or 17, we have the development of strands, but unlike those cases, the strands here, the apparent strands developing here, are much wider, and they take up a large part of the loop. This gives us a clear sign that the loops tend to become rather turbulent if they are driven. You can also see that in this video here, where we have our three models, and we just present the cross-section at the apex. Again, for the impulsive standing mode, nothing new. We already seen that in the past. However, the driven case are much more interesting. The tweak rolls developed there actually expand and they throughout the cross-section of our loops. What does it mean? It means that we cannot really talk about separate core regions and layers, in this case at least. We should be very careful when we try to study the effects of heating or dissipation, and we're focusing mainly on a layer, because that layer might not exist. The whole loop might be a giant layer at that point, full of turbulence. This, by the way, is part from our submitted work of Karamelas and van Dorselaere. Hopefully you'll hear more about this in the future. here I would like to show you what we found about the energies in our system. We show here the input energy that we give through the driver. We show the internal energy, the magnetic energy, and the kinetic energy, and the sum of kinetic, magnetic, and internal. There are quite a few things that could be discussed here, but the most important one that I would like to focus on is the relation between the magnetic energy or energy density and the internal energy density. Now, before saying anything else, I have to clarify that these are volume averaged quantities, but they are over a stable volume, a constant volume. So I'm going to use the term energy and energy density interchangeably, but they're exactly the same thing here, qualitatively. So what we see, especially if we compare the driven equal T model and the driven diff T model, is that there is a strong connection between the magnetic field energy and the internal energy. What we see is that in the case of a temperature gradients, the magnetic field drops much more, the magnetic field energy drops at a higher rate, and at the same time the internal energy rises beyond what it did in the case of a uniform temperature. Actually, the internal energy seems to get the same levels of the input energy that we give to our system. And that's a strong indication that hinting towards Joule heating. However, this is just a hint. We don't know anything yet. And therefore, I would like to show this picture here. Again, it's about the models with a uniform temperature. And what I'm showing here is the volume averaged square current density, Z current density, on the left, and the volume averaged squared Z vorticity on the right. What we see, or what we can see, is that the current densities are getting higher and higher the closer we get to the foot points, while at the same time the vorticity is getting higher and higher the closer we get at the apex. Now, this is not a universal feature. This takes place here because of the geometry of our oscillation. We have an oscillation that resembles the fundamental standing kink mode, so because of that, the geometry affects these results, and this is why we have stronger currents near the foot points and stronger velocities here near the apex, which gives us these contributions. Again, though, these are two hints. If we get a very high temperature near the foot point, then we would expect it to be due to resistive heating. Again, if we find larger temperatures near the apex, they should be because of the viscosity. This is also the case for the rest of the other two models that we have. So the results that we're going to find should be applicable to everything, to all three models considered here, of course. Now, before showing this, before showing the final results, I would like you to have a look at the resistive heating rate and the Z vorticity as we have measured it along the radius of our loops. So these are quantities averaged for each radius. And what they say is that, again, the vorticity near the apex shows us that we have a very turbulent cross-section. Nothing new here. We've seen that before from the contour plots that we have. Whereas near the foot points, the vorticity is located at the layer. So again, nothing new here. If you remember how the foot point looked like, we didn't have much turbulence there, almost none, because we should not have any chemical stability near the foot point. It's stable. On the other hand, the resistive heating rate near the foot point is spread throughout the cross-section. It's not limited into a very thin, narrow layer at the edge. So if we have resistive heating at the foot point, this should take place throughout the cross-section. Again, if we have viscosity and viscous heating at the apex, this should take place throughout the cross-section. This is really important because should we consider radiation, then we need an energy source, a heating source inside the loop, because the most heavy density, heavy core region of a loop would deplete faster due to radiation. And this is a way that we can work around this problem and give enough heating there as well. Again, this is part of our submitted work. Hopefully you will see it soon. And this is almost the final and most essential part of our results. What we see here is on the left, the driven equality model, so the model with a uniform temperature, and on the right, the model for with a temperature gradient. We have the volume average temperature over height and over time for all the duration of our simulations. What we see on the left is that we get a rise of temperature mainly near the foot point. There is a very small heating taking place at the apex, but comparing to the foot point, it's negligible. And what does this say? What we have already discussed so far, that this should be the effects of resistive heating. I cannot be 100% certain because, let's be honest, no one can be 100% certain about anything, but with what we saw so far, this is a very valid assumption that resistive heating is responsible for this temperature increase. Now, on the right, actually we don't really have anything new. We knew that already since 2016 from the work of Magyar and Van Dorselaere. Again, we have a higher temperature gradient, a higher temperature increase at the apex, because the apex is turbulent. We have extensive mixing, we have hotter coronal plasma getting inside our loop, so the temperatures are bound to increase. What we see here is that the apparent mixing that we see on the right is much higher than the actual wave heating that we get on the left. However, this is due to the energy that we gave to our system, and to have correct quantitative results, we should implement a realistic driver, and we should give a realistic amount of energy in a physically acceptable way to be able to compare the two values. This is just a mapping of the energy dissipation taking place inside the loop. So, for the summary, we have pretty much already discussed most of the conclusions, so I won't go through them again. You can read them. Mainly, I would like to focus on the future steps. We are currently working on gravity, thermal conduction, and physical dissipation parameters like resistivity and viscosity. We are running simulations as we speak with those results, and I will study them more as soon as I get back to Leuven. The last two steps, however, are going to be addressed hopefully in a future work. And these are the two steps where things are getting really, really interesting. Thank you.
First of all, I would like to thank you for holding such a beautiful event. And it's amazing, guys, being here in such a beautiful city. Let's start now. Many people cannot agree on whether small-scale heating events, impulse events, can hit the corona or not. And this is because statistical studies do not agree either. Our goal in this talk is to show the synthesized observational traces of small-scale events identified in MHD simulations of the solar atmosphere, and to show why they're so confusing. Students just draw attention to me. What we call actually Joule heating events are actually regions that exhibit a high probability of magnetic reconnection. And this is because they describe a highly resistive medium where we have highly distorted magnetic field, as described through this formula. These regions could be somehow correlated to flaring events, even though it's quite an optimistic approach. One may ask, why did you choose Joule heating events to quantify the energy release? I know that. To quantify the energy release on magnetic reconnection in your simulation. At magnetic reconnection sites, we have plasma flowing from the one direction and accelerated to the other direction. And and current sheets can be formed in these regions. When these current sheets are thin, then the particle acceleration is large, and large gradient of velocity is also formed. Therefore, the heating, we have viscous heating that dissipates the magnetic energy far away from the reconnection sites. In contrast, when these current sheets are thick, then the particle acceleration is small, and the viscous heating is almost insignificant in respect with Joule heating because the particle acceleration is smaller as well. Since our simulation resolution is not of the order of meters, therefore we can assume with some safety that because of the fact that our current sheets are few hundred kilometers thick, that the main contributor on heating the solar corona in our simulation is Joule heating. An important statistical property of the impulsive heating events is the formation of distributions of the occurrence of frequency of such impulsive events in respect with the energy they release. And this is a power law. And people do not agree because they don't agree on this power law index as well. In order for the nanoflares, or better for the small scale events to be important, then this slope needs to be larger than 2. However, it depends on many factors that complicates stuff. Factors as like how do you define an event, how did you observe it, and which instruments you have used, etc. As an example here, we show in this table that different research studies have found through years different slopes. In this image, we display the identified Joule heating events in the corona, and this is a Bifrost simulation we use and where we have used also a relatively new method of identifying 3D local enhancements in our data. Those events show also, those are impulsive events, and the residual of this region, imagine that as a constant medium, is slow burning current sheets. Like other studies, we also identified a slope less than 2, and this is attributed to our small scale events attributed to 5% in this example of the total Joule heating, while the residual could be a combination of unresolved heating events, which we predict is rather a tiny fraction, and slow burning current sheets, which are formed which can be formed from any mechanism that can distort the magnetic field, such as waves passing. What I like to call these residual regions, I rather like to call them slow burning current sheets because they exhibit a coherent structure with non-eruptive disruptive character. In our study, we use 3 tools to explore how these Joule heating events look like in observations and compare them with the case where we have assumed information from the total column mass of the corona. First tool are the intensity maps for the 6 extreme ultraviolet filters of Aya. The second is time lag maps calculated when cross-correlating these filters. And last is the emission measure by using the electron density and temperature computed by the Bifrost code. This GIF represents how loop-like structures and strands in the lower image looks like at different Aya filters, which represent emitting plasma, radiated plasma at different temperature spectra. The top image, we see loop-like structures rising from the bottom and extending in higher heights, while in these structures we can see strands in the lower image that have compilation of, no, we don't see compilation of motions, but we can see strands. In the between space of these strands, there is this diffuse region or slow burning currents. In this short image, we can see in the lower panel a combination of motions of the strands. Some strands are blend with their neighbors, some others are emerging from the bottom and merge with some others that are just standing there, while some others just diffused in a matter of small time scales. However, all the information is hidden by the diffuse region of the top image. What we can also do with intensity maps is to track intensity in time at fixed positions. For instance, here in the top image, we can see the three positions along a loop-like structure, as you can see in filter 171. For the case where we assume information from the total column mass of the corona, while the second is for only parts of the column mass that exhibit these impulsive events. Red lines represent the information of the total column mass, while blue lines represent informations from the impulsive only cases. What we can see here is that red lines have a smooth flickering, they fluctuate smoothly, while blue lines have an intermediate character of a small short-lived burst. We have also identified different number of heating events depending on the region we observed throughout the total time investigation, which is more or less 1 hour. And we have concluded that the number of events is not linearly correlated with the intensity with the red line. Lateral motions play also an important factor of how loops look like. To do that, let's isolate one filter and let's take a look. And we place a slit, a 3 millimeter slit above a loop-like structure, and we trace the intensity of that, and we plot distance time maps of intensity, and we can calculate the velocity, lateral velocity of a loop for short slits. And what we found here for the specific loop is a lateral motion of 2 kilometers per second, which is also validated when looking the velocity field in the code. Most importantly, this is the case where we see only impulsive events, identified impulsive events. We can see along the loop forming short-lived bursts, and we concluded that are part of the loop moving together. However, the intensity is much less than the total column mass, and again, the information is hidden in these loops. Time lag maps is another tool we use in our analysis, and they're used to identify the cooling or heating sequences of radiated plasma as observed through different filters. This is an example of the time lag maps between these two specific IR filters, and we can see 0 positive and negative time lags. 0 time lags may be actually due to the overlapping between the responses functions of each IR filter. Cooling in this specific case is represented with green shades, while heating is represented with purple shades. In the case of the total column mass, we see coherent structures in the middle where between the two polarities. We also see that the negative time lags heating is not so apparent. In contrast, in the case of impulsive events, the picture of the game changes. What we see here are seemingly elongated structures extending around the two polarities and in their between space. But most importantly, we see small, short-lived bursts grouping together and having similar time lags. This grouping actually suggests that impulsive events are connected together with their neighbors through probably an avalanche model. Also, in this case, we can see negative time lapse, which are indicating heating. And the literature suggests that this heating appears when an impulsive event appears during the pulsive phase of another event, or at least before the first event cools down. Lastly, emission measure maps illustrates emitting plasma at specific temperature ranges, and it is calculated through this formula. And when calculating the emission measure from only parts of the total column mass that exhibit flaring events and compare that with the information we received from the total column mass, we see that the first one is much less than the second one. And how emission measure is distributed along height is what we will see in the next slide. What we see here is a cool, low-lying plasma, while relatively hotter plasma appears higher in the corona. Hotter plasma appears higher in the corona because impulsive events can happen in larger numbers there. And this is because magnetic field drops with height, and therefore it's easier to bend and distort the magnetic field. Strong heating also appears above the strong magnetic structures, where it's really hard to bend the magnetic field, but when it does, due to the high magnitude of the magnetic field, large amount of energy appears. We can see also low-lying loops here that are usually forming in regions of where the magnetic field is very small, which is between the two polarities, where it is diminished. We can see similar structures of the case of the total column mass and for only flaring cases, which again, information from here is hidden under the carpet of this case. In summary, information from heating and cooling due to impulsive events in the quiet sun is overpassed by that of the diffused region. We have seen similar and different features in both regions, how they might differ and how they might be correlated. And this has been done in various observational tools. Those, my friends, are evidence showing why it is difficult to derive a conclusion on whether small-scale heating events can hit the corona or not. Thank you.
Postdoc at the University of Sheffield, and today I'll be talking about essentially the signatures of cancellation in the solar atmosphere. So this work will basically be split down into two separate sections, as in the title. We've got small-scale bursts in the photosphere, so the lower solar atmosphere, and then also cancellation, potentially leading to the filling of coronal loops in the last few slides. But that's just a preliminary work at the moment. So the motivation behind this work, which I've been working on for a few years, was essentially, initially, to do with small-scale bursts. It was to do with things like element bombs and iris bursts, UV bursts in SDO channels. And these are very dynamic events. We've already seen this movie earlier in the week in the Bill Fraser's talk. And we've got this element bomb here, and it's very dynamic. And ever since we've been able to observe these events co-spatial with line-of-sight photospheric magnetic fields, people have found that they generally occur at locations of at least strong magnetic fields, if not at inversion lines themselves. So what I wanted to do is basically analyze how the magnetic flux evolved at those regions. And then recent work, just published this year, has shown that cancellation can also be observed at coronal loop foot points. So that was done using sunrise data, which is very high resolution data, but unfortunately it's limited in the amount we actually got. So I wanted to have a look to see if we could find similar evidence of such processes using the more ubiquitous HMI data. As it's 100 years since the original publication, just a quick plot. This is the ADS citation history from Elements 1917 paper, and this year on his centenary has reached 100 refereed citations. That's quite nice. So if we look at an active region, essentially we have these strong positive polarity magnetic fields, we have the strong negative magnetic fields, and what we have is this process that we call cancellation. So what do we actually mean by cancellation? Well, we don't mean that it's a physical thing. Cancellation is not talking about one specific physical thing. Essentially, it's just the disappearance or the reduction in the amount of magnetic flux we measure at a specific location through time. So there are actual multiple physical processes which can lead to cancellation as we observe it. For example, magnetic reconnection or flux submergence, or in this case, when we're just measuring the line of sight magnetic field, it could be a reduction in the line of sight magnetic field, but not actually a reduction in the total magnetic field. So here we're just going to measure the properties of cancellation. So we're not looking at these big polarity regions like the sunspots and the pores. What we're going to look at is these smaller regions like around here. And this is over the course of about 40 minutes. You see the positive polarity magnetic field and negative polarity magnetic field interacting. And as they interact, this negative magnetic field is going to disappear. And what we want to look at is the actual properties of that disappearance. So as it's HMI, we can combine this very neatly with the AIA instrument, and we can get a good understanding of what's going on at multiple heights in the solar atmosphere. So, as we saw in the movie, over the course of about 30 minutes, these two opposite polarity magnetic fields come together. The negative polarity magnetic field and the positive polarity magnetic field both reduce in the amount of flux they have, until eventually in the final frame there's no flux from the negative polarity observable. As this happens, we get this burst event in the photosphere. So as this negative polarity magnetic field approaches the positive polarity magnetic field, something's happening to create this extra emission in these photospheric lines. And it's hypothesized that this is some sort of photospheric magnetic reconnection, an energy release like that. And we don't see any signature in the chromosphere. So this is a burst observed with the SDO instrument, the AIA instrument. So we don't actually name this beyond just calling it a UV burst, but the typical properties of it are very similar to element bombs. We see a signature in the photosphere, so with element bombs that's an increased emission in the H-alpha line wings, but we don't see any signature in the chromosphere. So the element bombs, the line core is exactly the same in an element bomb as outside of an element bomb. So it's thought that this is a photospheric release of energy, which is leading to this increased emission. So if we measure the actual flux at these locations, which is the top panels, we can clearly see this reduction, which goes at the rates of about 10 to the 14 or 10 to the 15 maxwells per second. Generally, the locations that we observe these flux regions, initially have magnitudes of the order of about 10 to the 18 maxwells per second. So they're really quite small in terms of solar magnetic features. So if we calculate the amount of magnetic energy that disappears from the start of the observation to the end of observation, we get around 10 to the 24 ergs, which is very similar to the estimated radiative losses of element bombs through their lifetimes. So it's quite nice. It ties together quite well. And in these plots, you can see quite a nice correspondence between when we have cancellation, for example here, you see this rapid reduction in magnetic flux, and where we get these burst events in the photospheric channels. So here you can actually see this rises of the magnetic flux as well, and that corresponds to when more flux comes from further away, and it combines with the systems that we have, and that's often called sort of a feeding of the flux. And very often that occurs co-spatial to element bombs and UV bursts. We have these opposite polarity magnetic fields which interact with the fields that we already have, leading to this energy release. So as these are small events, we're talking about the size of 1 arc second. It's also important to question whether we're actually resolving this quite well, or with the HMI instrument and the AIA instrument, or whether we're losing a lot of the actual information that we have. So here's a nice movie of an element bomb observed with the SST, the CRISP instrument. and we have the element bomb in the blue wing of the H-alpha line. And on the right-hand side, we have the Stokes V component, which is essentially the line of sight magnetic field from the iron 1 6302.5 line. And what you can see is that at the inversion line between where the positive polarity magnetic field and the negative magnetic field interact, we get this element bomb, which occurs. And it's very dynamic. It's changing of the order of every 10 seconds. The next frame, it's very different than how it was before. So, in collaboration with Aaron Reed in Belfast, we looked into how the reduction in the magnetic field in these SST data compared to what we had with HMI. And he performed some inversions. So we have the element bomb in the top left-hand corner, the Stokes I of the iron line, and then the Stokes V of the iron line. And using the inversions that he was able to do using Nicole, where he fitted these line profiles, we were able to estimate the actual magnetic flux at the locations of these element bombs. And it was found that the cancellation rates were the order 10 to the 15. And we compared that directly back to the HMI signatures at those locations, and we found that it was very, very similar, the amount of flux that we were losing. So it seems like HMI is catching a lot of the information at those locations. So just briefly, iris bursts, which were also briefly discussed earlier in the week, they also occur co-spatial to this cancellation of the photospheric magnetic fields. But that's to be expected if the majority of iris bursts and the majority of element bombs are occurring in the same locations. You'd expect that they would have similar signatures in the photospheric magnetic field. So essentially these small-scale bursts, in terms of the magnetic polarities at their foot points, generally have quite similar properties. The flux elements have initial strengths of around 10 to the 18 Maxwells, and they cancel at around 10 to the 14 or 10 to the 15 Maxwells per second. So the second half of my talk is essentially some preliminary research that I've been working on, and it's looking at cancellation at the foot points of coronal loops. So this is the observation from Sunrise, where you have the positive and the negative polarity magnetic fields, and the resolution of this instrument was much better than we can get with the HMI instrument. And what the authors found was that essentially wherever they identified these loops in the SDO-AIA instruments, they were able to see that there's small parasitic opposite polarities which are interacting with the larger negative polarity here. And they suggested that it could be that the actual flux cancellation or the reconnection that might be indicative of is actually driving mass and energy into the corona to fill the loops which are at those locations. And they also found cancellation rates around 10 to the 15 Maxwells per second. So like I said, we wanted to look into essentially more ubiquitous data to see if I can find some more examples of this we can also see in HMI. So I started off by looking at essentially transient loop systems. So these are coronal loop systems which only have lifetimes of the order of 2, 3, 4 hours. And these are plots from 2007 from Lopez Fuentes' paper. And these were observed using the SXI instrument on GOES. And they could see that the initial intensity of the loops is quite low. There was nothing there. This was a background level essentially. And it rises up. The intensity stays at the loop level for a few hours, and then it fades away. So if the cancellation at the foot points of these loops is important, we should see that essentially we get a cancellation beginning at the foot point, as the loop starts to rise in the intensity, was the thinking that I was having, so which was what I was looking to test. So I went through the some SDO data, some AIA data, and I was looking for these transient loops, for example in the 171 passband. And I found a few examples where we don't have anything, and then over the course of a few hours, this loop system appears, and then, as we can see in the light curve, around 9 o'clock, the intensity increases, stays at that level for around 2 hours, and then it decreases again. And this is the actual magnetic foot points of this loop system. So we have the positive polarity is routed around here. The actual box here isn't perfectly aligned to this one. I just realized I didn't have an actual map of the magnetic field in here yesterday. So I took an image of HelioViewer and estimated. But this foot point actually corresponds to this positive polarity field here. And this foot point up here corresponds to this bipole up here, essentially. You've got the negative polarity magnetic field and the positive polarity magnetic field. So we're starting to look quite hopeful that we might find similar results in this sense. So what we'd expect is between this frame, essentially 9 o'clock, and between this frame at 25 past 9, essentially, we would expect some sort of cancellation to occur at this foot point if this cancellation process is going to be important in filling this loop system here. So essentially, we went through and we calculated the magnetic flux at these locations, we plotted them through time, and we did find a small reduction in the negative polarity magnetic flux at this foot point, and at the positive polarity magnetic flux at this foot point. And they were essentially fairly similar. The differences between this flux and the small scale events we talked about earlier was that these fluxes are actually at the scale of around 10 to the 19 Maxwells. So they're actually an order of magnitude bigger than what we were observing before. So again, we found cancellation rates of the order of 10 to the 14 or 10 to the 15 Maxwells per second. But what we found was very different observational results than what we discovered previously. The small scale events, the small scale cancellations, apparently the 10 to the 18 Maxwells, they were giving us these small scale bursts, lifetimes around 10 minutes, and sizes around an arc second. Whereas these larger scale cancellation at the foot points seem to be giving us this large coronal loop structure. So that's ongoing work at the moment, looking into this, but a couple of potential scenarios. So it's just preliminary thoughts. We've either got filling from the photosphere, as was suggested in the original paper, where the reconnection is happening in the photosphere and it's driving jets and it's driving mass up into the atmosphere, potentially similar to the prominences that we've already discussed earlier in the day. Or perhaps we've got some sort of reconnection in the photosphere and in the corona, and what we're seeing is the actual signature of that in the line of sight photospheric magnetic field. And I've been looking into these, and I have my own personal preference, but I won't say what it is yet. I'll still look into that. But that's ongoing work at the moment. So just the conclusions. This photospheric cancellation is observed throughout the atmosphere. We see it in active regions, we see it in quiet sun regions, and it has a variety of observational signatures. But for the events that we looked at, for the different types of features we looked at, we got very similar cancellation rates. Well, it didn't really depend on what we were looking at. And these cancellation rates are also very similar to what people have measured at the foot points of surges and things like that. We also found these localized short-lived coronal systems do seem to occur cotemporally to cancellation, and it could be that this cancellation is similar to the smaller scale cancellation that was observed by Chitter et al. In their coronal loop systems. But the remaining question is what is this photospheric line of sight cancellation actually indicating in terms of a physical process? So thank you very much.
So basically we know that the solar wind has two components, the fast wind and the slow wind. And this is measurements by Ulysses that show how the fast wind looks at solar minimum. And it looks quite steady and fast at 800 kilometers per second. Slow wind has a more complex structure where you have many streams of different velocities that are mixed together. So the motivation for this study is to understand how the solar wind is formed, in particular focusing on the fast wind component. Now, another strong motivation is the upcoming Parker Solar Probe mission that will actually measure or provide measurements inside the inner heliosphere, if you can define it as within 30 solar radii. And as you can see, these are the science goals of this mission. And the first one is to trace the flowing energy that heats the solar wind and accelerates the solar wind. So this is basically a process that has been studied for decades, but is not well understood. Now, typically when we look at the solar wind magnetic fluctuations, we see this kind of fluctuation spectrum where this is the power density, energy density, and this is the frequency. So we have at very low frequencies, we have f to the minus 1 spectrum. Then there is a range of frequencies where we have this f to the minus 5/3 or a turbulence range. But this is all fluid regime. Now, when we approach the cyclotron resonance, the spectrum is steepened. So this is the cyclotron resonance of the protons. We're not even talking about electrons and stuff. So now the goal is to focus on the kinetic regime. So where we already have the fluid energy going into the energy of the particles. So the heating of the particles is basically collisionless because there aren't too many collisions beyond several solar radii. They occur through various wave-particle interactions. So here are some typical spectra that one sees of these fluctuations. So this is from ACE, and you can see this is the break point here. And this is at 1 AU, this is closer to the sun. You can see again for different components you have the inertial range where there is no dissipation basically, because there are no viscosity or resistivity or anything like that. In the heliosphere, and the dissipation range where the dissipation is through kinetic instabilities. Now, interestingly enough, similar spectrum is seen in the inner corona, of course without the dissipation range, but this is from comp data by Tomczyk and McIntosh. And they do see this power spectra as well, with additional contribution from PIMO. So, moving forward, the other important property of the solar wind is that when you basically tabulate your measurements, where you look at the temperature and isotropy versus the parallel temperature. Now, for those of you who don't work on solar wind, it is often anisotropic, so the temperature along the magnetic field could be significantly different from the perpendicular one. And all these points sort of form this shape. So interestingly enough, the boundaries of this shape of the parameter space could agree very well with the known kinetic instability. That means if we have, let's say, very high anisotropy and low beta plasma, the plasma will be subject to the mirror instability or cyclotron instability in some cases. So then you don't see much plasma in this unstable region, and most of it is in the stable region. This is another measurement from ACE, so you can see similar structures. So these instabilities are important in shaping the properties of the plasma. Now, if you look at the velocity distribution functions, again, when we talk about fluid, we usually assume Maxwellian distributions, but these are highly non-Maxwellian, especially in the fast wind. What you see here, this is measurement from Helios spacecraft. You can see this is the magnetic field direction, that the spread in the perpendicular direction is very large compared to the parallel. So this is an isotropy. And in addition, you see evidence of beams. For the ions, this is for protons, and even worse, in a sense, from departure from Maxwellian for the alpha particles. So then, how can we study these things? Obviously, well, there are several approaches. I don't have time to review all of them, but the approach we use is hybrid modeling. In this approach, the protons are treated as particles, where we solve the equations of motion subject to the background magnetic field and electric field for millions of particles, while the electrons are still treated as a fluid, because the time scale, their resonant frequency is 2,000 times faster or larger than the proton one. So then we use the electron momentum equation in the approximation of zero inertia to solve for the electric field. Then we have Maxwell's equations, and then this is called particle in cell for the solution of the ions, where we update the location of the ions every time step, and then the fields in a two-step process. So then the problem is when you deal with kinetic scales, then your spatial scales are also quite small. So the parcel of plasma typically that we deal with is of several thousand kilometers extent in the heliosphere. So in the next slide, let's show the situation. So you have this parcel of plasma that expands in the heliosphere. So in order to model the effect of expansion as this parcel of plasma is stretched, the coordinates become time dependent. So then we can incorporate the solar wind expansion to the coordinates in there, and we'll talk a little bit more about that. So then, show you some results with a hybrid model. Again, it's a brief overview. So then we have a plasma that consists of alpha particles and protons, and we inject a large amplitude alpha wave. So here what you can see is the time evolution of this velocity distribution. So you can see this anisotropy here that is increasing for alphas as well as for protons, and then you see the formation of the beam. This is the extent that you can see here, where the direction of the magnetic field is parallel. Now this is these are the velocity distribution functions, but you of course can use them to calculate the moments, all the fluid quantities. So here, in the next slide, here's another result of this 2D hybrid model. It's actually 2.5D, so we do have two spatial directions, and we allow for magnetic field and velocity components out of the plane. So here what you see here is this initial drift between the protons and alpha particles is often observed in the solar wind, but this drift is increased artificially to get faster evolution of the instability. So what you see here that the drift very rapidly relaxes to much smaller values consistent with observations, and at the same time the protons undergo perpendicular heating as well as the alpha particles. But the alpha particles are heated very rapidly to very high perpendicular anisotropy, so they undergo secondary instability. Now these colors represent different expansion rates of the solar wind. So if you consider a faster expansion, then the perpendicular heating will be suppressed. For slower expansion, this is will be slow. So the fact that the parts of the plasma expand also affects the evolution of the kinetic processes. Now we can construct the various power spectra. So they are all in the dissipation range, so we can see that they are highly steep. And then we can also construct a dispersion relation just by looking at the spatial and temporal variability of the magnetic field components. So you can identify in resonant mode as well as resonant modes in the dispersion relation. Now the simulation also produces the breakpoint, as you can see, because some of non-resonant frequencies are also included. So what you see here, this is for protons, this is for density fluctuation, this is for parallel velocity fluctuation. You can see clear evidence of the breakpoint at the proton gyro frequency, which is normalized as 1 in this model, and this is for the alphas, which is 0.5. So you can recover a lot of these properties of the observed plasma. So recently we looked at the effects of the drift where we had non-uniformity to the drift profile, because we know that the solar wind plasma is non-uniform across the field, of course along the field as well, but across the field it could vary on smaller scales. So this is our velocity profile, and then we have a drifting population of the alphas with respect to the protons. And what you see here is an example of such a solution where we start, these are the protons, these are the alphas, and you can see that as the drift evolves, because of the instability, basically this shape of the enhanced flow is suppressed, very much like we see in the fluid instabilities when we have Kelvin Helmholtz. But here it's not Kelvin-Helmholtz because there's no time for the Kelvin-Helmholtz to evolve, which evolves on orders of magnitude slower time scale than the drift instability. The next slide shows an animation of the evolution. So you can see on the left the protons and on the right the alpha particles due to this drift. Once more. So you can see the larger drift in the alphas and then the generation of small scale waves and the suppression of the drift by the magnetosonic drift instability. If you look at the magnetosonic waves, you can see the magnetic fluctuations associated. This is the Vx component, this is the Vz component associated with the waves produced by the instability. Again, these waves by themselves, they also resonate with the particles, so eventually they get absorbed. These are just 3 snapshots of 30, 40, and 50 Jarrett periods. So this is another example where we have a smoother velocity profile, and what it shows is the magnetic, the generation of the magnetic wave components. This is the velocity profile of the smoother case. Now, the interesting thing is that now we can, in this model, we can also look at the velocity distribution functions of various parts of the simulation. So typically these simulations are homogeneous in blocks, but now we have different regions, so we can see the differences where in region 1, which is the low shear region, and this is the high shear, and this is the high velocity region. So you can see the differences in isotropy and the departure from the Maxwellian distribution. You can also look at the formation of the non-thermal tails in the perpendicular direction due to the effects of the drift. Now, as well as previously, we can construct the dispersion relation. This dispersion relation, again, is not a solution of any linearized equation. This is just from the hybrid model where we look at the magnetic fluctuations in space and in time and then Fourier transform them. So we see that all the magnetic fluctuations arrange along these curves. So we can identify the non-resonant mode, the resonant polarized mode of the ions, and then the magnetic fluctuations, and then the resonant modes. And as you can see, as you go to higher Ks, they dissipate. This is symmetric on the left. So we see these processes that we integrate very well with the loss of linear solution. We see directly from the linear solution that we have the resonant and non-resonant mode. We can identify the proton mode, the alpha mode, and so on. We can also find the generation of oblique waves. So this is our parallel direction, and we can see that we also start having waves. This again in the Fourier space, we start having waves in oblique modes. So to sort of again, we can use the results of the simulations for diagnostic of the magnetic fluctuations. We can construct the dissipation spectrum where we have this non-uniform flow, and we can look at the different components of the energy, the perpendicular energy growth due to the instability and parallel of the alphas. And we can also compare the cases for different parameters. So if you have a sharper Gaussian, so we have stronger heating and less sharp Gaussian case. This is for gradually growing instability. Now, recently we expanded this model into full 3D. So this is some preliminary result of 3D hybrid model where we have a cube. This is just test run was 64 cube, but we already did some high resolution runs. And this is a comparison of 2D and the 3D modes, and you can see that the evolution for this case is quite similar as expected because of the parallel propagating waves. So the 3D structure, although it changes the evolution time scale, but not by much in this case. So to summarize, so you have observations that show that there's a fast and slow wind, and actually both contain magnetic fluctuations and evidence of waves. But in addition to what we know from the studied so far in the fluid regime, when we start to look deeper, we see non-Maxwellian velocity distributions, isotropic temperature, drifting ion populations, and effects of kinetic instability. So then this needs to be modeled properly in order to study the heating, which is a collisionless heating basically, in the solar wind. So aided by observations from previous missions that went to 0.3 AU, but now we will have in the near future the Parker Solar Probe that will provide data in the acceleration regions of the solar wind, to be up to 10 solar area. So there we should see evidence in the velocity distributions and in the magnetic fluctuations, the evidence of the acceleration mechanism and the evidence of the waves that possibly come from the corona and accelerate solar wind. So just to summarize the results of the present study, we find the solar wind expansion affects the perpendicular cooling, so it has to be supplemented by resonant wave heating, and that the small-scale background in homogeneities can affect the dissipation and affect the heating of the small-scale structures in the solar wind. Thank you.